Hello, calculus kids! Welcome back to another lesson in calculus. This is Mr. Bean, and today we'll focus on related rates. For those of you who don't know anything about this, you don't know what you're about to get into. I will tell you at the end of the year when kids look back, usually this topic is the thing that kids struggled with the most. If they think, okay, what was the hardest thing we did this year? Often it is related rates. So I really need you to have thinking caps on today. Let's try to learn as well as we can some strategies to help you solve these. Now, this step-by-step guide here, this is not exactly how you perfectly are able to solve. These are just guidelines. Every problem could be a little bit unique depending on the situation that we're thrown into. But these guidelines will get us some skills to help us solve most of the problems that we're going to deal with. So I'm going to refer back to these 5 steps, or these 5 guidelines, I should say, not steps, that's a bad way. And then I have a boxed important thing here that is on your notes, that substituting a non-constant quantity before differentiating is not allowed. You're probably like, what the heck does that mean? I don't expect you to know what most of this means yet, so let's just jump into a problem and see how we do it. So first thing is, remember to draw a picture. So let's read our easy example number 1. The width of a rectangle. Okay, so we're going to have a rectangle. So I have this rectangle, and it's not increasing at an exactly constant rate, both the length and the width. It says here that the width is increasing at 2 centimeters per second, and the length is increasing a little bit faster. So what that means, let's see if I can get this, what that means is that it is growing faster this direction than it is this direction. Okay, so it's a moving or a dynamic rectangle here. It's changing. So at what rate is the area of the rectangle increasing when its width is 4 and its length is 5? What are we supposed to do? Draw a picture. We did. There's our rectangle. So draw a rectangle on your picture. Now, we're going to make a list of all the known and unknown rates and quantities. So here we go. You ready? What I'm going to make a list of first is that we're increasing at a rate of 2 centimeters per second. The width is. So if I were to call this the width and this the length, and this whole thing is the area, then I'm going to have that the rate of change of the width. So I'm going to say that dw dt, the width is changing with respect to time, is going to equal 2 centimeters per second. You can write the labels or you can just put the number. We just got to make sure that all of our units are the same. Next we have the length. The length is increasing with respect to time at a rate of 3 centimeters per second. So we have this first one, we have the second one, and at what rate is the area of the rectangle increasing? So this is what I want to do here. I'm going to put that they want to know the rate of the area with respect to time. So I'm going to put an equals question mark, and I'm putting a box around this thing to remind myself while I'm working. I like to do this to remind myself the whole point of the question is to figure out what rate is the area of the rectangle increasing. This is what I'm looking for. At the exact moment when W equals 4 and L equals 5. All right, so I have a list here of all of my known and unknown quantities and rates. Let's go back and look at this. All right, so now the next step, number 3, relate the variables in an equation. This, of all of the things on this list, this is the one that kids struggle with the most, figuring out how to relate them in an equation. So I started off with an easy one. I have these variables W, L, and A. So how do you relate width and length and area in an equation? Real simple. It is that the area is going to equal length times width, or width times length. It doesn't really matter what order. So that is how we relate them in an equation. Now we differentiate with respect to time. So you're going to take the derivative of this whole entire thing with respect to time. So the derivative with respect to time. This is implicit differentiation. That's what we practiced in the last lesson. Differentiating everything with respect to time gives us, okay, so the derivative of a is just a 1, right? But then we have to do times the derivative of a with respect to time equals WL. So I'm going to do product rule. So I'm going to ignore this 1 times part. I'm going to do that part for all of this. So the product rule, derivative of the first, so I'm going to have dw with respect to time times L, I'm not touching L, plus, and now I leave the first one alone, so I'll leave it as a W, and then I do the derivative of L with respect to time. Now I have a formula. All of these things, I took the derivative, and so we did number 4, differentiate with respect to time. Now we substitute the known quantities and rates and solve for dA dt. So we're trying to get dA dt by itself, which it already is. So dA dt equals, now substitute stuff in that we know. What is the rate of the width? It's 2 centimeters per second. At the time when the length is 5, we're going to add at the time when the width is 4 centimeters, and then the rate of the length is changing at 3 centimeters per second. So we plug in a 3 here, and this all works out to 10 plus 12. So the dA dt, we'll rewrite this here. dA dt is equal to 10 plus 12, 22 centimeters per, centimeters squared, because we're doing area, centimeters squared per second. So we want to make sure we get the correct units. And there's my final answer, which we were looking for, which goes back to this box question marks that I was trying to remind myself for later, that's the final answer. So 22 centimeters squared per second. Okay, easy example number 2. So we have this thing happening where we've got a police car here, and it's going that direction as it's chasing a speeding car that is going this direction. So the police car is approaching the intersection, the speeding car is going away from it. So you kind of read through this to make sure you understand what is happening. As I go through, I'm going to try and figure out what is the question it's asking. If the police car is moving, blah, 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 what is the speed of the car? What is the speed of what car? If the police car is moving at 60 miles per hour at the instant of measurement. So I have found it useful to try to label some things with variables. I'm going to call this side y and this side x, which just makes sense because it's kind of like it's on the x-axis and it's on the y-axis for my picture. Let's see. So what else do I want? Let's label some things. At the exact moment when the police car is 0.6 miles north, so at the time when y is equal to 0.6, and the car, so the speeding car, when we say the car, we're talking about the speeding car, is 0.8. So x is going to equal 0.8 miles to the east. The police determined with a radar gun that the distance between them, that's this dashed hypotenuse, and the car is increasing at 20 miles per hour. So why don't we just call this z? And it says that it is increasing. So that means the rate of change of z, so we'll call it dz dt, is equal to 20 miles per hour. As long as this is miles per hour, this was miles, okay, everything's going to work out okay. I'd have to make sure I'm careful with my units of measure. So if the police car is moving at 60 miles per hour, so the y is moving at a rate of 60 miles per hour, the police car is. This is the part that throws kids off. So watch what I'm about to do. The rate of change of y is not equal to 60, it's equal to negative 60. Why? Because why? Y is getting smaller. The police car is approaching the intersection, so y has to be decreasing. So we can't just say that it's 60 miles per hour, or else that means the police car would be going away from the intersection. It'd be going this way. We don't want that. We want it to be going towards the intersection, which means that y is decreasing, so we say negative 60 miles per hour. So what is the speed of the car? So we want to know how fast is x increasing. This is what we are looking for. I'm going to box this thing to remind myself dx dt is the final solution that I want to have. Okay, let's set this stuff up. So we drew a picture, made a list of all the known and unknown rates of change. Now we're going to relate the variables in an equation. What type of variables do I have? I've got an x, y, and a z. So x, y, and z. How do you relate this? Well, if it's an intersection, and we're assuming it's a right angle, right-angled intersection, then we use the Pythagorean Theorem. X squared plus y squared equals z squared. Okay, take the derivative with respect to time. That gives us 2x is the derivative of this. dx dt plus the derivative of y squared is 2y times dy dt equals the derivative of z squared is 2z times dz dt. Okay, plug stuff in. I'm going to speed this up a little bit. Okay, so we have some problems. One, we don't know what dx dt is. That's not really a problem because that's the whole point of this whole scenario anyways, to figure out dx dt, how fast the speeding car is going away. But we don't have z right here. We had a variable that we ended up with that we did not have a quantity for. So when this happens, you have to actually figure out what z equals. So we are going to take x squared plus y squared equals z squared and use this right here to figure out what z is at the moment when x is 0.8 squared plus y is 0.6 squared, and that equals z squared. So when you solve for this, you get z equals 1 at that exact moment. So now we can clean this up. Again, I'm going to fast forward this a bit, plug in a 1 here. I have dx dt increasing at 70 miles per hour. And again, that was what I was looking for. They're trying to figure out the speed of the car moving away. Okay, so the big trick on this one was two things for this example that we did that was different. That was one, we had a negative rate of change, so we had to be careful about the signs of rate of change when you do these problems. And then we had a quantity that we didn't know, so we had to use the equation we set up for a relation to figure out our unknown variable. So sometimes that happens in these as well. Now we're going to get into a couple examples that are not so easy. So here we go. Rocket is lifting off at the Kennedy Space Center. If you want to pause and read through this problem real quick, go ahead. I'm going to assume you've already read this as I start drawing this picture. So I'm going to draw some type of triangle and say that this is 2,000 feet. Okay, now this is a value that is not going to change. I want to go back to the very beginning when I had here substituting a non-constant quantity before differentiating. What this is talking about is you can't plug in the numbers. Substitute, you can't substitute any numbers in if it's a value that's going to change. But here with this example, the 2,000 feet, this will not change. You have a camera that's down here and the rocket is blasting off, so I have my rocket that's going up in the air here. And that camera is watching it. The distance here is not changing. We're not moving the camera back and forth. So this 2,000 is a set constant. Everything else is going to be changing in this triangle. Okay, so I need to move this over a little bit. What else do we have? The height of the rocket is found using s of t equals 50t squared. This height, we're going to call this s. Now, s is equal to 50t squared. I also could have called it 50t squared, but I'm just going to leave it as s for now. So s is feet, t is seconds. Find the rate of change in the angle of elevation. That's what we're looking for, this angle of elevation of the camera. So we'll call it theta. So what we're looking for is t theta dt. In fact, I'm going to move that over here a little bit to keep it out of the way. d theta dt equals question mark. That is what I'm looking for. So the only way to get an angle is if we use some type of trigonometry, sine, cosine, tangent, to relate everything we have. Okay, so how about, let's see here. What can we make a list of? We have 2,000. What else? We've got S. Oh, at camera of 10 seconds after liftoff. So we want to say when t equals 10 seconds. Well, if t equals 10 seconds, how high is the rocket? That means at the moment when S equals, plug in a 10 here, you get 10 squared. That's 100 times 50, that's 5,000. So when the rocket is 5,000 feet high. So 10 seconds, 5,000 feet high, that's what S is. What else we got? I think that's it for now. Let's see what else we can come up with. See if we can do an equation of how to relate these things. So if I have an angle, opposite, and adjacent, that's tangent. So tangent theta is equal to opposite, which we'll call S, over adjacent, which is 2000. Okay, we have our equation. Let's differentiate with respect to time and see what we can come up with. So the derivative of tangent is secant squared theta, and that's going to equal, remember that S over 2000, that's the same thing as 1 over 2000 S. That right there is what this is. Okay, so when you take the derivative of that, it just becomes 1 over 2000. So this is 1 over 2000, and then we have ds dt, because we're doing implicit differentiation. Oh, I forgot to do that over here. My bad. We got to multiply a d theta dt, because you have to do the derivative of the inside. So I did the derivative of tangent theta. I forgot d theta dt. Big mistake there. Important to keep track of all that stuff, which is probably good because we were looking for d theta dt anyway. Okay, so now what's going on? We need something to plug into theta, and we need something to plug into ds dt in order for us to solve for this. So we have two variables that we need. What is ds dt? Well, it's the derivative of s. And if s equals 50t squared, I'm going to write this down here, then ds dt is equal to 100t. Now I could do dt dt, but dt dt is just, so we don't need that part. So ds dt is 100t. So let's clean this up a little bit. Remember that secant squared is the same thing as 1 over cosine squared. So that's what secant squared is. So if I multiply both sides by cosine squared, then I'm going to get theta dt is equal to, this is great news, we've got it by itself, cosine squared theta. This is over 2000, well, I'll just leave it as a fraction, times 1 over 2000. And then this ds dt, what's that? It's 100t. But we already know that t equals 10. So it's at the time where we have 100 times 10. So again, ds dt is 100t, so this is 100t. Okay, next step, d theta dt. What is cosine? So cosine is, remember, adjacent hypotenuse. So if we have the adjacent, which is 2000, over hypotenuse, we've got to know what the hypotenuse is. Oh man, so the hypotenuse, let's write this right here. The hypotenuse, if we use Pythagorean Theorem, is square root of 2000 squared plus s squared. That's the hypotenuse. Okay, hopefully you can see what I'm doing here with the Pythagorean Theorem. So cosine theta, remember it's cosine squared, so I'm going to write this with a squared. We have a fraction, and it is adjacent, which is 2000, over hypotenuse, which is the square root of 2000 squared plus s squared. This is getting a little bit sloppy here. Now here we can clean up. I'm going to grab my calculator and discover that this cleans up into 1/2. And then what is this? We're almost done. This probably was going to, you're going to probably want to use a calculator to help you a little bit here. The s, what does s equal? S is at the moment of 10 seconds, which we wrote down here that this is 5,000. So it's the rocket's 5,000 feet in the air. So we plug a 5,000 in here. So d theta dt is equal to 2,000 squared. Holy cow. And then divided by 2. So 2,000 squared divided by 2 is 2 million. What? That's a big number. 2 million. And then down here, the squared just goes away. So I have 2,000 squared plus 5,000 squared. That's 29 million. 0, 0, 0, 0, 0, 0, 0, 0. So then that's going to equal, the millions are all cancel, so it's going to equal 2 over 29. That's my final answer. And what are my units? I'm talking about angle of elevation. So again, we're working in radians in calculus, so it's 2 over 29 radians. Radians per, now what are we doing? We got to look up here. What did we do? T is in seconds. So 2/29 radians per second. So as the rocket increases and is flying straight up in the air, the angle of elevation of the camera is having to change by, at that exact moment, at 10 seconds, to over 29 radians per second. Holy cow, awesome problem. Go to our last one. This cone example you'll see appear once in a while in different textbooks, and a big reason is because back in 2002 there was a problem that was similar to this on the AP exam, and so ever since then a lot of calculus teachers want to make sure they cover it because it was so hard for kids. So I'm going to show you how to do this one, and you'll see why it was a challenge. First of all, water running into a conical tank. So we have this tank. Water is pouring into the thing, so we're dumping a bunch of water in. That represents volume. So you got to know right away that this represents how much the volume is changing by. So I'm going to write down that the derivative of V, the derivative of volume with respect to time, is increasing by 9 cubic feet per minute. The tank stands on point down, okay, and the height, and has a height of 10 feet. So this whole height here is 10 feet and a base radius of 5 feet. So the question is, how fast is the water level rising? So this water is going up, 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 up. So dH dt, that is what they are asking for, question mark. At the exact moment, hold on, box this one. At the exact moment when the water is 6 feet deep, so when the height is 6, when this right here in blue is 6 feet, at that moment, how fast is the water level rising? Okay, so notice we have the derivative of volume, the derivative of height, and we have height. There's no radius anywhere in this formula. So we have V equals blah blah here, but we have no dr dt. We don't even have what r equals. We do have that the base of the radius, this top here, this part is 5. We know that. So let me show you what we do. What you have going on is two different, let me get rid of all this. You have two different rectangles. Can you see, or I keep saying rectangles, triangles. So we have a big triangle like this, and then you have a little triangle like this. Horrible triangles, but you get my meaning. So the big triangle has a height of 10 and a radius of 5. So what that means is that these triangles are similar triangles. They have exactly the same proportions. So the proportion of 5 to 10 here is the same as this proportion r to h. So let's do it like this. So I have some h here and some r here. It's going to be changing this h and r. What I can do is say that 10 over 5 is equivalent to h over r. Or in other words, 2 is equivalent to h over r. Now, why is that so important? Because it would be really nice when we take the derivative of this equation, when we differentiate this, instead of having an r squared and an h, it'd be real nice if we only had r's or we only had h's. And the reason we are allowed to do that is because of this situation right here. We can say that 2r is equal to h. So if we wanted, we could take 2r and plug it right there into h and have only r's. Well, now we don't want to do that because over here you can see the variables and information we have is we're looking for dh dt, and we know what h equals. So instead, we want to say that r is equal to h over 2. And if we know that r equals h over 2, then I can rewrite this volume equation. So let's rewrite it down here. I'll just start right here. Volume equals 1/3 pi. Now instead of r squared, I'm going to substitute in what r squared equals, which is h over 2 squared, and then times h. Let's clean this up a bit before we take the derivative. So let's see, we're going to have, once we clean this all up, I'm going to have a fraction of pi over 3 times 4 is 12 h cubed. All right, that's my volume equation only being in terms of the height for this cone. Take the derivative of this and we get dv dt equals 3 comes down. 3 pi over 12 reduces to pi over 4. So you can do this long ways. I'm just trying to do this fast, but 3 comes down. 3 pi over 12 reduces that fraction, and then we get h squared dh dt. and then we're going to plug in all of the information that we have. So dV dt, the volume is increasing by 9 cubic feet per minute, equals, we have pi over 4 at the exact moment when the height is 6 feet squared. Then we're looking for dH dt. Okay, so when you clean all of this up, and this becomes 36 over 4, you get 9, you divide both sides, you're going to end up with 1 over pi. So 1 over pi feet per minute. If you want to show your steps on this one, you can show that a little bit more. I did that faster because I'm running out of time, and this video lesson is taking forever. So this is what the rate of change of the height is. 1 over pi feet per minute. You could figure out the decimal if we wanted to go that way, but I think we want exact answers if we can, if it's at all possible. Okay, we finished this lesson. What I'm going to do is I'm going to actually do a little walkthrough for every single problem on this practice set. So you can click the links below, just follow below where you see the solution and solution links, and I can show you if you really get stuck on any of them how to do these problems. All right, rock that mastery check. See you back in the next lesson.